Hi there, this is Calculus Integrals, and we're going to be hitting on the topic of definite integrals. This is the first video of that. So basically there's a few just essentially conditions that I want to kind of follow up on, and for us to be able to do definite integrals. So for definite integrals, first of all, the integrals. Okay. For us to be able to do the definite integral, first of all, the function must be continuous within the range. So, continuous within the range, right? That's key. And someone might ask, like, hey, well, what does that mean? Well, essentially, all I'm saying is that, well, you have some kind of function right here between A and B. It has to be continuous. It can never just, like, lop off or not make sense in one section. It needs to make sense all the time. And here's an example of when it wouldn't make sense. You know, you go this, and then right here it goes like this. So notice how it just kind of hops to B. It's almost like you need to describe them separately to make any sense of it. But yeah, so just realize that this gap is not appropriate, and this is not continuous. So continuous and not continuous. Alright. In terms of sometimes there are situations where you'll have a continuous graph, whatever shape it may be, but then at one segment, say like at C, it will not make sense. And you can actually give your solution just like you would regularly, but you would say this is not valid for such and such. So it is possible to have a conditional basis as well. So, and also some of those will sometimes look like this. Whereas at C, once again, it seems like it goes to infinity and it never really hits it. So just realize that these can be they can be considered not continuous between A and B, and sometimes you need to make them conditional. So another thing is that if you remember from our previous video, first of all, that this layout right here, f from B or A to B, f of x dx equals the limit as n goes to infinity of essentially the sum of this, which is n, and this, I'm going to just say I equals 1. So the idea is that essentially this value at a given f of x, whatever x may be, times the delta x, which is the increment. And this is the layout for essentially integrals. And let me just run you through an example that is really simple to do. Let's see, we're going to make a little graph here. Okay. And I'm just going to do it right here. This spot, this spot, this spot, and let's see. We can do it probably one more time. Oh, let's extend it just for fun. So this would be 1, 2, 3. Let's do 4. I think that'll be enough of an example. So let me just draw this line right here. And this line essentially describes the function y equals 1 minus x. And the thing is that when I ask for the integral of this between 4 and 0, we know that of 1 minus x, we know that we can actually do multiple things. One, we could just determine what the area is underneath these curves between 0 and 4, or 0 and 1, and 1 and 4. That makes two triangles, which essentially, if I were to label this as A1 and this is A2, A1 would equal 1/2 times base times height, and A2 would equal 1/2 base times height. So when you combine these two together, you'll get 0.75 plus 3.5, that's 4.25 as an estimate. Or actually, that would be exact. So then what we need to do is, well, what if we did like a box estimate? I mean, we could try and do that, right? And what you would find is that you do get significant error when you do draw this out again. When you draw this out, you'll find a lot of this business. There's no, this isn't scale or anything, I'm just trying to give you some idea of what it looks like. And essentially, all of this, all of this, all of this, all of this, and all of this, this is all air. Air. And actually, right here and right here, these two are also air. So this technique may not be the best. So what we could realize is that, what if we made these, if we sent delta x to 0, and then, or in other words, we sent n to infinity, and then we could actually do what we knew integrals of as before as antiderivatives. So what if we took the antiderivative, I'm going to keep it in integral form, but the antiderivative of 1 minus x. Now, realize that we should probably split it up to both area 1 and 2, just so that we can kind of segment it. Alright, so the area between 1 and 0 at 1 minus x, well, that is just going to equal x minus 1/2 x squared. Well, between 1 and 0, you'll find that it is just 1 minus, what is it? Just going to be 1/2, right? Minus 1/2 times 1. And then you're going to have zeros for the other ones. So it'll just be 1 minus 1/2, which is 0.5. And then you would do it again for the other area. And just doing that would give you kind of a good roundabout feeling for it. And you just do the same exact thing, 3 to 1, and then just the same integral, which is going to equal the same thing. You're just doing it from different points, right? So 3 to 1, and you would solve for that. Now, I'm running out of space, but I just wanted to make sure that I didn't make an error up here, up at the top. The area of this is going to be 0.5. The area of this is 3 times 3 divided by 2, which is going to be 9/2. That's your 4.5. So then what you should have is this and this add up together. Excuse me, I didn't mean to have that there. Let's do the summation of this, which is 5. Thought that 4.25 sounded a little odd, but that was just me being dumb. So okay, basically watch your work and just keep practicing at this and watch the next video. I think you'll find it useful.